We will continue with our discussion on vector operations. In the last class, we saw how a vector could be resolved along its Cartesian components, and we used I, j and k with a hat as symbols for unit vectors, where I was a unit vector along the x axis, j was the unit vector along y axis, and k is a unit vector along z axis. And what we showed was how a vector A can be written as AXI plus AYJ plus AZK. Similarly, if we have a second vector B, then vector B can also be resolved along these components. So, vector B can be written as Bxi plus Byj plus Bzk. An advantage of resolving vectors along the Cartesian axis directions is that once we resolve the vector along these directions, the addition of vectors can then be very easily done. So, if we have expressed vectors A and B like this and we want to find their sum. So, if we want to find A plus B, then they can be it can be written directly as Ax plus Bx times I plus Ay plus By times j plus Az plus Bz times k. And simple, if we have to add up even these vectors multiplied by a scalar or something subtracted by a scalar, then we can follow similarly. So, for example, 2 times A minus 3 times B, if we have to find this sum. So, this will be equal to 2 times AXI plus AYJ plus AZK minus 3 times BXI plus BYJ plus BZK. So, this will be equal to 2AX minus 3BX times I plus 2AY minus 3BY times J plus 2AZ minus 3BZ times K. So, therefore, resolving a vector along components along Cartesian axis may help us in simplifying some of the operations. Next, we will also look at products of vectors. We have seen the addition of vectors, we have seen subtraction of vectors, and we have seen also when a scalar is multiplied to a vector, how do we deal with that. Next, let us talk of products of vectors. Now, here what we see is that sum of two vectors is a vector, but we cannot say the same thing for a product. And actually, you will see that at this level we can say that there are two ways of defining product of vectors. That means, we define two different type of products. Now, so we define two different types of products of vectors. And here what we will see is that both these products, they satisfy the distributive law of multiplication, that is product of A and B plus C. So, we take A multiplied by B plus C, this will be equal to product of A and B plus product of A and C. And so, let us first define the first type of product. The first type of vector product which we define, that is a product of two vectors, we call that as the scalar product, or because we use a symbol dot for this, this is also called the dot product. Now, how do we define this? So, we have two vectors, a vector A and a vector B, and let us say when we place the two vectors with their tails together, the angle between them is theta, and this angle is the smaller of the two angles, because angle between A and B, somebody could also look at the reflex angle which is formed between A and B, but we look at the smaller of the angle. So, therefore, this angle theta will be between 0 and 180 degrees. So, we look at this now. The scalar product of vector A and vector B, this is defined by, this is given by multiplying three quantities. The first one is the magnitude of vector A, the second one is the magnitude of vector B, and the third one is the cosine of the angle between A and B, that is cosine of theta. And so, what we write is, we denote this as vector A and we use the symbol dot, A dotted with B, this is equal to magnitude of A times the magnitude of B times cosine of theta, where theta is, as I have explained, the angle between A and B. So, this product, because all these are scalar, this product is a scalar. So, dot product is always a scalar. So, now we look at some properties of the dot product. So, the first property we see is a scalar product is commutative. What this means is A dotted with B is equal to B dotted with A, and this is obvious from the definition of the product of this, because A dotted with B, this will be equal to magnitude of A times magnitude of B times cosine theta, and this will be magnitude of B times magnitude of A times cosine theta again. So, therefore, these will be the this is what the dot product will look like. Okay. Now, while A dot B is a scalar, so the second property we see is, while A dot B is a scalar, it can be either positive or negative. So, it can have a sign, and this will depend on the angle. Magnitude of A will always be positive, magnitude of B will always be positive. So, the sign will depend on angle theta. If the angle theta is between 0 and pi by 2, then A dot B will be positive, and if theta lies between pi by 2 and pi, then A dot B will be negative. So, Now, some other things which we look about this, if we look at a dot product of a vector with itself, A dotted with A. So, this will be nothing but magnitude of A times magnitude of A times cosine of 0 degrees. So, this will be nothing but magnitude of A square, or the square of the magnitude of the vector is the dot product of the vector with itself. The second thing, let us see, if A dot B is equal to 0, then what we see is either magnitude of A must be 0 or magnitude of B is 0, but if these we can call as trivial cases, but if that is not so, then cosine of theta must be equal to 0, and for cosine of theta to be 0, this will give us that vector A has to be perpendicular to vector B. So, therefore, if the dot product is 0, then the two vectors have to be perpendicular if either of them is not 0. And sometimes this is also used to prove that two vectors are mutually perpendicular. If you have to prove this, then you take the dot product, and if you get the dot product as 0, then you can show that A is perpendicular to B. And we also sometimes use a special term. We say that vector A is orthogonal to B. Instead of saying perpendicular, so this is a terminology which we used. Now, the third thing, if we look at scalar product of two unit vectors will be cosine of the angle between them. So, then we have already seen the commutative property that dot products are commutative. Then we have another property which is the distributive property, about which we said, which was taken care of. If we look at A dotted with B plus C, then this will be equal to vector A dotted with B plus vector A dotted with C. Now, let us look at how this dot product looks in terms of unit vectors. So, let us look at the unit vectors I, j, k along the Cartesian axis. So, when we look at these, then clearly if I look at I dotted with I, this will be 1. Similarly, j dotted with j will be 1 and k dotted with k will also be 1. But if I look at I dotted with j, this will be equal to cosine of the angle between I and j. So, this will be 0, I dotted with k will be 0 and j dotted with k is equal to 0. So, now this can be used to expand and write the dot product in a general way. So, for example, if we have a vector A is equal to, let us write this, if we have a vector A is equal to AXI plus AYJ plus AZK, and vector B is equal to BXI plus BYJ plus BZK. Then if we want to write the dot product, then A dotted with B, we will write it, and so we will use the distributive law to expand these. So, this will be equal to AXI plus AYJ plus AZK dotted with BXI plus BYJ plus BZK, and so now we expand each of these terms again. The first term gives us AX BX times I dot I plus you will get AX BY I dot J plus AX BZ I dot K, and then we can expand this, we will have a total of 9 terms. in these 9 terms what we will see is I dot j, this will be 0. Similarly, I dot k will be 0. This second term, maybe let me expand this fully, this will give me ay bx times j dot I plus ay by j dot j plus ay bz times j dotted with k, and then plus az bx k dotted with I plus az by k dotted with j plus az bz k dotted with k, and continuing our these things, j dotted with I, k dot I will be 0, k dot j will be 0, j dot k will be 0, and each of these I dot I, j dot j and k dot k will be 1. So, finally, what we get is a dot b is equal to, in terms of components, ax bx plus ay by plus az bz. So, this is how we can work out. Now, if we look at the triangle law of cosines, so we can easily show this using the dot product. If we have a vector A here, vector B, the angle between them is theta. If I now plot this one, this vector is nothing but vector A minus B, and let us call it as C, because when I add B to this vector I get the third side of the triangle, which gives me A. So, this vector which I have called as C, the third vector is A minus B. So, clearly we can write vector C is equal to vector A minus B, and if I write it in terms of magnitude, then magnitude of C is equal to magnitude of A minus B. So, now what we do is, let us take this first expression, let us take a dot product of C with both sides, or so we will write dot product of C with C is equal to A minus B dotted with again C, which is equal to A minus B. So, we write it in this form, and what we have here is, so if we expand this we get C dotted with C is equal to A dotted with A plus B dotted with B minus 2 times vector A dotted with B, where we have used the commutative and the distributive properties. So, now if we write this C dotted with C, this can be written as magnitude of C square is equal to magnitude of A square plus magnitude of B square minus 2 times magnitude of A times magnitude of B times cosine of the angle between A and B, which is theta, and magnitudes are nothing but these lengths of the sides. So, we get C square is equal to A square plus B square minus 2AB cosine theta, which is the cosine law for triangles. And what we also realize is that cosine of the angle between, if there are two vectors and if they make an angle theta, so cosine of the angle between vectors A and B, this can also be written as A dotted with B divided by magnitude of A times magnitude of B. So, therefore, if we have to find the angle between the two vectors, then we can take the dot product of the two vectors and divide it by the magnitude of these, that will give us the cosine of the angle between the vectors. We use the dot product in many circumstances, and one of the quantities where you will come across dot product will be when we talk about mechanics and we talk of work done by a force or the power due to a force acting on a point. When we talk of these quantities, work done and power, we will see that these quantities are nothing but dot product of two vectors. For example, work done will be defined as force and a dot product of force with displacement of the point on which the force is being applied, and similarly power will be defined as the dot product of force and velocity of the point on which the force is being applied. So, this is how we will use dot products, and other quantities involving dot products will come in the course. Now, suppose we have a vector A which is given by Axi plus Ayj plus Azk, and we want to find unit vector which we represent as E sub A with a hat along A. Now, the unit vector we know will be given by a vector which is of magnitude 1 along direction A. So, this unit vector E sub A will be equal to vector A divided by the magnitude of vector A. And to find the magnitude of vector A, what we will do is, as we have seen, we will take dot product of A with itself. So, that will give us magnitude of A square, and dot product of A with itself will give us Ax square plus Ay square plus Az square. So, therefore, we can easily say that magnitude of A will be square root of Ax square plus Ay square plus Az square. Therefore, unit vector along A, this will be equal to Ax I plus Ayj plus Azk, and this will be divided by magnitude of A. So, we divide this by square root of Ax square plus Ay square plus Az square. So, this way one can, given any vector A, one can find the magnitude of vector A. Suppose we are given a vector A and we have to find component of A along a direction EB. That means some direction is given where EB is a unit vector along that direction, or we could say we want to find the component of A along B. So, then this component is given by vector A dotted with EB. This gives us the component of A along B. Also, in many problems you may need to find the component of A which is perpendicular to EB. So, we may also need to find component of A perpendicular to EB. So, in that case what we will do is, first we will take vector A dotted with EB. This will give us component of A along EB. Now, this is a scalar. So, what we do is we take A dotted with EB along with the vector EB. This we can refer to as the vector component of A along EB. And now, if we want to find the component which is perpendicular to EB, then vector A minus A dotted with EB times the vector EB, this will give us the component of A which is perpendicular to EB. So, this may be needed in some problems, but one thing we have to realize that if we talk of component of a vector along a particular direction, this we can get by taking, this we obtain by taking dot product of the vector with unit vector along that direction. Now, if I take the component of the same vector along a second direction, I can do it by taking dot product of this vector with the unit vector along the second direction. Now, the sum of these two components will be equal to the original vector only if the component directions are perpendicular. If they are not perpendicular, then we will not get the original vector A again. In fact, that will actually lie somewhere between 0 and 2 times the original vector. So, the sum of the two components being equal to the original vector will only happen if the components are mutually perpendicular to each other. Now, having seen the first type of product, let us look at the second product, a second type of product, which is called the vector product of two vectors. Now, this product is also called the cross product. Now, as we saw in the scalar product, the product of two vectors was a scalar. In this case, the vector product of two vectors is a vector quantity. It is not a scalar, and in advanced courses you will also see that this is a vector in a rather restricted sense. But for our purposes, we will just take it like this, that the vector product of two vectors is a vector. Now, how do we write this? Suppose I have two vectors A and B, as we had before, the same vectors A and the vector B. So, we define a product which we now use the symbol X or cross, A cross B, that is what we call it. This is defined as a vector which is, first we give its direction. The direction of this vector is normal to the plane containing vector A and vector B. That means, it is A and B, two vectors will always make a plane. A cross B is a vector which is perpendicular to this plane. Now, first let me talk about the magnitude, because this normal itself can have two directions and the direction of that will be explained in a moment. So, the magnitude of A cross B, this will be equal to magnitude of A times magnitude of B times sine of the angle between A and B. So, if we call the angle between A and B as theta, then the magnitude of A cross B will be equal to magnitude of A times magnitude of B times sine theta. And let me call this as a vector C. So, now what we can say is the vector C can be written as a unit vector along C times magnitude of A times magnitude of B times sine theta. We still have to explain what is the direction of C, which will give us EC. So, the direction of C is determined by the right hand thread rule, and this is a fixed convention which we use. So, what we do is we have the vector A, we have the vector B. So, what we rotate the vector A towards B by the smallest angle between them. Once again, we will look at the smaller of the angle between A and B. The other angle will be always a reflex angle. So, we look at by the smaller angle between A and B. We rotate A towards B. Now, those of you who have seen screws, when we rotate a screw, the screw moves in an axial direction. So, if I move A towards B and the screw has a right handed thread, then the direction in which the screw will move, that will give us the direction of A cross B. So, we rotate A towards B, and the direction in which a right handed screw will move, that gives the direction of A cross B or C. Now, there is one more way in which we can look at this, and that is what we call as the right hand thumb rule, and which is easy to see for everyone. So, what we do is we place the two vectors, this is vector A, this is vector V, we place the two vectors with tails together, and now notice when we are doing this, we have to carry out this exercise with the right hand. So, if most of you who are doing this, if you are right handed, drop your pen when you are doing this exercise. If you are holding your pen, most likely you are doing it with your left hand, which will give you the wrong result. So, this exercise has to be done with your right hand. You take the right hand, and what you do is you make the fingers of your right hand curl in the direction when A will rotate towards B through the smaller angle. So, in this case A and B are like this, we rotate the right hand in the direction from A to B, and the direction of the thumb gives me the direction of A cross B. So, here so we place the two vectors with tails together and curl the fingers of right hand in direction from A to B, and when we do that, the direction of the thumb points towards A cross B. So, now you will notice if I am doing A cross B, that means I am turning from A to B, my thumb is pointing inwards or downwards, as you would see. Now, if I do B cross A, that means I put my fingers at B, turn them towards A. Now, you will notice the thumb is pointing upwards. So, therefore, B cross A and A cross B, they point in the opposite directions. A cross B points in opposite direction to B cross A. That means we can clearly say A cross B is equal to minus of B cross A. And this also tells us that this product is not commutative. The dot product was commutative, but this one is not. The second thing which we observe about this product is that if we look at A cross B plus C, the distributive property still works. This is equal to A cross B plus A cross C. Then if we look at A cross A, this will be equal to magnitude of A multiplied by magnitude of A multiplied by sine of the angle between A and A. Now, because A and A are the same vector, sine of this angle, the angle between A and A will be 0. So, therefore, A cross A will always be 0. Not only that, if we have two parallel vectors A and B, Then also, so if this is one vector A and there is another vector B which is parallel to A, then also you will see in this case A cross B will be equal to 0, because the angle between these two vectors is 0. Now, the Cartesian axis which we have been drawing, which I have shown to you, which we used in the last lecture also, if we talk of this as the x axis, this is the y axis, this is the z axis, then you realize they are always right handed in the form that if we rotate from x to y, then the third axis z axis will point in the direction of the thumb. So, the Cartesian axis as we draw these, when we draw them in 3D, we always draw them as right handed. And a consequence of this, as you will see, if we now write the unit vectors I, j, k, then clearly I cross I, j cross j and k cross k, these will be all 0. But if we look at the products between the cross direction, that means we look at I cross j, this will be equal to k. And then if I look at j cross k, and for this to look at to show this, if I go from x to y, I point in the direction of z. Similarly, if I go from y direction to z direction, if I curl my fingers, then I am pointing upwards, which is the x direction, and if I go from z to x, I am pointing in the direction of plus y. So, we have j cross k is equal to I and k cross I is equal to j. And if you observe, these make a cyclic this thing, that if we put I, j, k in one order, then I cross j is equal to k, j cross k is equal to I, and k cross I is equal to j. That means, if we follow these I, j, k in a cyclic order, we will get the third thing will be positive. But if we go anti-cyclic, then we are inverting the directions, and clearly minus of I cross j is equal to minus k, and minus I cross j is also equal to j cross I. So, we have j cross I is equal to minus k, I cross k is equal to minus j, and k cross j is equal to minus I. So, when we do this, that means we are doing anti-cyclic. So, this is one way of remembering them, you can work it out like this. So, we have, let us see this, cyclic order is positive, and anti-cyclic, that means we go in the opposite sense, anti-cyclic order is negative. So, now let us see, if we have two vectors A and B which are expressed in terms of Cartesian coordinates, then we can use the full expansion and the rules developed to find the cross product of these vectors. So, then we can write A cross B as AXI plus AYJ plus AZK crossed with BXI plus BYJ plus BZK, and this one can then expand. So, this will be equal to AYBZ minus AZBYI plus AZBX minus AX BZ times J plus AX BY minus AY BX times K. And these follow the rules that I cross I is 0, I cross J is K, etc., which we have seen. Now, another way of seeing this is through the concept of the determinant, which if you have seen in your maths courses, then if we can write A cross B as the determinant of I j k Ax, Ay, Az. This is the first of the cross product. The second one we write as the third row, Bx, By, Bz. And if you know how to expand determinants, the first term, let me just show, it will be I times Ay Bz minus By times Az, etc. So, then this can be explained. Now, let us look at some applications of the cross product. The first one, if we look at the magnitude of A cross B. So, we have two vectors A and B, and if we look at the parallelogram which is formed by A cross B, then the magnitude of A cross B, this is given by magnitude of A times magnitude of B times sine of the angle between A and B. Now, this is clearly, if you look at this parallelogram, this is also equal to the area of this parallelogram. The magnitude of A cross B gives us the area of the parallelogram formed by the vectors of side A and B. So, this is magnitude is equal to area of the parallelogram with sides A and B. Similarly, if we have a parallelepiped which has sides A, B and C, that means if we, this is A, this is B, this is C. So, that means we complete this parallelogram, and with C we complete this. We look at this figure which is a parallelepiped with sides A, B and C. So, then the volume of the parallelepiped, this is given as, if we call this as V, then V is equal to A cross B dotted with C, and since these are three sides of the parallelepiped, if we move in a cyclic order, we will get the same thing. So, this is also be equal to A cross B dot C. So, this will be equal to B cross C dotted with A, and this will be equal to C cross A dotted with B. So, we can use the dot product and cross product to find the volume of a parallelepiped. Then in mechanics, we will come across the concept of torque or moment of a force about a point. So, suppose we have a point O and a force F is acting. So, there what we do is, if we draw a vector from O, we draw a vector from O to the line of action of the force F, and let me call this vector as R. Then we define moment of the force F about O. This is defined as the cross product of R and F. Sometimes we also call it the torque. So, therefore, the moment of the force will give us the torque, and cross product is going to be used there. Then we also find the use of cross product when we talk of a point charge, when we talk of a point charge moving with a velocity v in a magnetic field B, then the force on this charge is in the direction of V cross B. So, this is again we use the cross product to show this. Then also if we have to show that two vectors are parallel to each other, then we can take, if we show that the cross product is equal to 0, then the two vectors will be parallel to each other. Now, let us take a small example involving some of these vector operations. So, suppose we are given a vector B is equal to xi plus 3j and a vector C is equal to 2i plus yj. Now, we have to find x and y such that B and C are perpendicular to the vector D, which is equal to 5i plus 6j, and the second part says show that for these values of x and y, vector B is parallel to vector C. So, for the first part, what we have to do is, we are given a vector D and we are given a vector B where there is one unknown. We have to find x and y such that B is perpendicular to D. So, for part A, vector B is perpendicular to D. This implies, now D is, if you recall, is 5i plus 6j and vector B is xi plus 3j. So, since B is perpendicular to D, this implies B dot D is equal to 0. So, this will give us 5x plus 18 is equal to 0. So, x will be equal to minus 18 divided by 5. And similarly, we have C dotted with D must be 0 because C is perpendicular to D and C was given as 2i plus yj. So, C dot D will give us, when we do C dot D, so that will give me 2i plus 5i, so that will give us 10, and when we take y plus 6, so 10 plus 6y is equal to 0. So, y is equal to minus 10 by 6, or this is equal to minus 5 by 3. So, now what we have is, if we, for these values, vector B is equal to minus 18 by 5i plus 3j and vector C is equal to 2i minus 5 by 3j. Now, to show that B and C are parallel, so for part B, to show B is parallel to C, we take cross product. Well, there are many ways of doing it. One way is to take the cross product. So, let us first look at that. So, we take B cross C. So, that will be equal to this determinant I j k minus 18 by 5 3 0 2 minus 5 by 3 0, and this gives us k times minus 18 by 5 multiplied by minus 5 by 3 minus 3 multiplied by 2. So, this will give us basically is equal to 0 k. So, since this is 0, B and C are parallel. Another way of doing this is we can write the unit vector along B, we can write the unit vector along C, and if they are either parallel or anti-parallel, then we will get the same thing. So, we can just divide B by the magnitude of B and C by the magnitude of C, and if we get the same unit vectors or negative of each other, then also we can show that B is parallel to C. So, that is another way. Now, let us just show, suppose we are given, let us take a small example again. Suppose we are given vector A which is equal to phi phi plus 10 j. Now, find the component of A along vector B, where B is equal to 3i plus 4j, and the second part we say is find the component of A perpendicular to the vector B. So, here since we have to find component of A along B, so for part A, first find, I will just illustrate this, first find EB, and then we take vector A dotted with EB, and as we have explained earlier, then this will be component of A along B, and to find the second part, what we will do is we will take vector A minus A dotted with EB, and along with the unit vector B, this will be component of A perpendicular to B. So, this is how one can work it out. These are simple numbers and you can work out these answers. And one more thing, if you have to check the answers, the two vectors which you get, if you take a dot product of those vectors, you should get them to be 0 because they are mutually perpendicular. So, we have had a bit of detour from kinematics because we started looking at vectors. In the next class, we will look at planar motion, we will look at motion in a plane, and we will derive the expressions for velocity and acceleration, and then we will look at the case for constant acceleration and what we call projectile motion, where we have a body under the action of gravity.